So this problem involves effusion, which is different than diffusion. It's pretty much the same idea, is that gases are moving. They're moving at a specific rate. The difference between effusion and diffusion is just a matter of how the gases move. So in a situation where effusion occurs, you can imagine you have a container or a balloon and you prick a small hole, and the gases will seep out. They're going to seep out, like in a straight line out of this small hole, a small, tiny pinprick. The gases will seep out, come out very slowly in a straight linear form, as opposed to diffusion, which is, you just basically open the lid, and then they just start going around here and there everywhere. So while effusion is more of a gentle leaking, diffusion is like it just all goes everywhere in terms of the motion of the gas molecules. So here you just open it up, here it's just a tiny prick and the gases seep out. Well, how fast will they seep out, or how fast will they diffuse out random, willy-nilly, bouncing off one another? Well, it depends on the molecular weight. So how fast this occurs when you're comparing two gases really has to do with their molecular weight. Right, so the heavier the gas is, the rate decreases. Okay, so if you have a very heavy gas, it's going to effuse or diffuse, for that matter, a lot slower. A lighter gas, a little bit lighter, a little more faster, a little more stealth. Based on its low molecular weight, we would expect it to effuse faster or diffuse faster. So the rates is really proportional to the molecular weights. So in this problem, one thing you want to do when you do this problem is it's sort of a crisscross. That's the way the equations work. Effusion rate, it's Graham's law. So the rate of one gas, so I'll call O2, over the rate of Kr, okay, you can flip this, it's just a fraction. You have to crisscross it, but the relationship is based on the square root of the molecular weights. And it's going to be the molecular weight of O2 in the denominator, and then the molecular weight of Kr in the numerator. So that's what I mean by crisscrossing. Okay, you have to flip it and then put the square root on it, because the heavier gas effuses and diffuses slower, the lighter gas effuses and diffuses faster. Okay, so because of that, the rates are sort of are the inverse ratio, and don't forget the square root. That's called Graham's law. So the rate of O2 divided by the rate of Kr krypton is equal to the ratio of their molecular weights of krypton over oxygen. So I think I'll do that here. All right, so using my periodic table, I have it on my side here. Square root molecular weight of krypton is about 83.8 grams per mole. The molecular weight of oxygen, O2, is going to be about 32.02 or 32.0 grams per mole. The grams per mole cancel. Taking the square root of this, getting an answer of about 1.62. So oxygen will effuse 1.62 times faster than krypton. Right? Or if you want to do it the opposite way, if you want to flip it, the rate of krypton over the rate of O2 gas, you just flip this. It will be 1 over 1.62. Now this makes a lot of whatever that number is on your calculator. So this makes sense, right? So oxygen is at 32 grams per mole. It's going to effuse faster than krypton, which is at 83 grams per mole. Now how faster will it effuse? It will effuse 1.6 times as fast.